This is paper 2, video 8 for the February mock. The first topic we're going to look at on this video is vectors. So here we've got quite a complex question. It's been split down into two parts just to try and make this a little bit easier. So the first part, we're going to start actually looking at this little bit up at the top where it's got to do with ratios. So up at the top it's saying that PM to MQ, so this line here with the M here, is split in the ratio 2 to 1. So that means that this section here, P to M, represents two parts of the line, and this one down here, M to Q, represents one part of the line. So altogether here there's 3 bits of line, so effectively we split the line into thirds, with this top section being 2/3 of the line, and the bottom section from M down to Q being 1/3 of the line. Similarly, for PN to NR, so this line over here, this section, or this line should I say, has been split in the ratio 1 to 2. Therefore again, 3 bits altogether, 1 and 2 making 3, which means that that is 1 of the 3 bits, or 1/3 of the line, and this is 2 of the 3 bits, therefore 2/3 of the line. So it's been split into 1/3 and 2/3, same as this but the other way around. The next thing we're going to look at is this. So here it says PQ equals B minus A. It's told us that. Just to prove it though, to get from P down to Q, we would have to go backwards along A, so against the arrow, so that would be minus A. Along here, so along B, so plus B. Well, B minus A is just the same as minus A plus B. So yes, we've kind of proven that. Didn't need to, but just to show that we could. It then says show OM, so the line from here to M, is equal to this. My thinking here would be, well, to get from O up to P, we would go along A, and then we would go down this bit just from P to M. Now we said before that P to M is 2/3 of the full line. So we are going to go 2/3 of the line from P to Q. P to Q we've already been told is B minus A. So effectively we're doing 2/3 of B minus A. If we just try and neaten this up, we've got A plus 2/3 times B, so 2/3 of B, 2/3 of minus A, just expanding this bracket, will give us minus 2/3 of A. And neatening this up, we've now got A, take away 2/3 of A, would leave me with 1/3 of A, plus 2/3 of B, which is exactly what we wanted to show, therefore we've done that section of the question. For part B of the question, it now wants us to show that OMN is a straight line. In order to do this, what we need to do is try and show two things. We need to show that OM, the line going from O to M, which we've got here, and the line from O to N, so from here to N, so the full line, we need to try and show those two are parallel, and also that they've got a point in common. So the first thing I'm going to write down, OM, we've already shown this, OM is 1/3 of A plus 2/3 of B. We now need to know what the line ON is. Well, to do this one, what we need, to start off, I'm actually going to work out the full length of this line, because I know later on we're going to need a fraction of it, so I'm going to do the full length of this line to start off with. So just as a side note, PR, well, to get from P to R, I would have to go backwards along A, so that'd be minus A, and then along this bottom line, so going along that bottom line, I've gone along B, and then another 3B, so altogether that'd be 4B. And just to try and keep it similar to before, I'm just going to spin that round and call that 4B minus A. So back to ON. So to get from ON, what I would need to do to go from here to here is I would go along this line here, so along A, plus, and then go from P to N. Now this is just a third of that full line. So I would have a third of the full line from P to R, which we've just worked out here. So a third of 4B minus A. Now we need to neaten this up to make it look a bit nicer. So this would give us A plus a third of 4B. In order to do a third of 4B, we get 4/3 of B. A third of minus A will give me minus a third A. Neatening this up, A take away a third of A would leave me with 2/3 of A plus 4/3 of B. So we've now got the two lines. Now looking at these two lines, the first thing that jumps out is that actually if I were to double OM, it would give me ON. So I'm actually going to write that down. So OM, if I were to double it, it would give me the line going from O to N. That proves that the two lines are parallel. In order to prove what it wanted in the question, there is a straight line, we've got to state that they are parallel. So by showing this, we've shown the parallel, and then state one other thing, that both have a point in common, so both lines pass through O, which they must do, because it says O in the name of the lines. We've now proven that they're straight lines. However, if you're finding a lot of that tricky, don't forget you can get a lot of marks simply by showing some of the earlier steps with the ratios. Next question we're going to look at is all to do with sectors of circles. Now here we've got quite a large sector of a circle. All we need to do is work out the area of this shaded section. In order to do that, we need to consider what fraction of the full circle we are actually going to work out. So here, if this little angle here is 70, that would mean that the other angle, the actual angle inside the shaded part of the sector, that angle is going to have to be 290 degrees, because remember, your two angles must add up to make 360 for a full turn. To work out the area of this section then, we have got a fraction of the full circle. The fraction we've got is 290 out of 360, so the full circle. And then we'd have to multiply, or find that fraction, of the area of the full circle. Now if you remember, area of a circle is pi r squared, so it's pi times radius, the radius says here, just 1.6, so 1.6 squared. If you type all of that into your calculator, that straight away actually gives us the answer of 6.48 metres squared. And that's the main bit really we need to look at for sector of a circle, but it might include some bits to do with the sine rule or cosine rule, which we did on one of the earlier videos. The last topic we're going to look at is invariant points. Now an invariant point is simply a point on a shape that when you perform a transformation, whichever transformation it may be, does not move. So the first example we're going to look at is this one, where we are going to enlarge by a scale factor of 1/2, given the centre C, this shape. Well, if we try and enlarge a shape given the centre, that simply means that the centre is the point that does not move, whereas all of the other points would now be half as far away. So for this one, because this line going up to B goes through diagonally these kind of 4 squares here, half of that would mean that the new point, sometimes known as B dash, would go there. For D, half the length of this line, well, half the length of this line would actually put the new point D just there. and A up here. Well, A is along 4 and up 6, so it would now become somewhere here, so along 2 and up 3, so A dash. So the new shape would look something like that. Actually, all of this working was quite unnecessary. To show which point was invariant, the point that didn't move, we simply need to look at where the shape was enlarged from, so the centre. C is the only point that hasn't moved, therefore which point is invariant? C. The second example of invariant points is this one. So this time to do with a reflection. Now it says the quadrilateral above is to be reflected in the line y equals x. Now you need to remember this, but the line y equals x is simply the straight line where joining all the y coordinates and x coordinates together that are the same. So it goes through the coordinate 1, 1, 2, 2, 3, 3 and so on. So very poorly drawn here without a ruler, you get something along the lines of that. Now if I were to reflect this shape in that line, B would move somewhere down here, D would move somewhere up this side, A moves over to the other side, so somewhere up here. The only point that wouldn't move is C, because that is actually on the line of reflection, the mirror line. So because that is on the line of reflection, C does not move, therefore when it says which vertex is invariant, which point doesn't move, C again.